We start by reviewing special theory of relativity. The dynamics of a moving particle in non-relativistic mechanics is represented by specifying the position of the particle at each point in time. The position is represented as a point in a three-dimensional space, and time is assumed to flow homogeneously. The position of the particle at a particular time can also be represented as a single point in a four-dimensional space. The position represented by a set of three position coordinates and time by the fourth coordinate. So we have a four-dimensional space consisting of three spatial coordinates and one time coordinate, and this four-dimensional space will be called a space-time. And the position of a particle at a particular time can be represented as a single point in the space-time, and a point in the space-time is called a space-time event. A trajectory of a moving particle corresponds to the specification of the position of the particle at every point in time within an interval of time. So a trajectory can be represented as a parameterized line on the four-dimensional space-time, and we call such a line the world line. In non-relativistic mechanics, there is the notion of simultaneity of two events, even if they are spatially separated, if their time coordinates are the same. So it is possible to slice up the four-dimensional space-time into planes consisting of sets of events, all of them having the same value for the time coordinate. But in special relativity, the notion of simultaneity of two events applies only if the events occur at the same spatial point. There is no valid notion of simultaneity of two events that are spatially separated. And therefore, slicing up of space-time into slices of simultaneous events is no longer valid, and therefore the space-time has to be considered as a four-dimensional entity together, and not separately as three-dimensional space and a time axis. However, given a point, there still is the notion of the events that occur in the future of the current event and the events that occur in the past of the current event. Now we discuss classification of different regions of space-time in special relativity. For this, we assume an inertial coordinate system set up for the space-time, which consists of three position coordinates along three Cartesian coordinate axes, x1, x2, x3, and the fourth coordinate corresponding to the time, and we call it x4. And this x4 will be equal to c times t, where c is the speed of light in vacuum. So together, an event in the space-time will be represented by these four coordinates, the three spatial coordinates x1, x2, and x3, which are measured using a Cartesian coordinate system, and x4, which is equal to c times t, and this time is measured by clocks that are that are attached to every Cartesian grid point in the space-time, which are initially assumed to be synchronized. Once we set up such a coordinate system and we consider two events A and B with coordinates given by say x1a, x2a, x3a, x4a, and similarly x1b, x2b, x3b, and x4b, we can define the coordinate differences dx mu to be equal to x mu a minus x mu b, where the index mu takes values 1, 2, 3, and 4. Then we can define a space-time interval ds square as dx4 square minus dx1 square minus dx2 square minus dx3 square. And this interval for an infinitesimally close pair of events may be written in the following form: ds square is equal to c square dt square, because x4 is ct and c is the speed of light, which is a constant, and therefore dx4 is c dt, and therefore we can write ds square as c square dt square minus dx square minus dy square minus dz square, where we have called x1 as x, x2 as y, x3 as z, as we do in the usual way of writing space-time coordinates in a Cartesian coordinate system, space coordinates in a Cartesian coordinate system. Now, in special relativity, this interval defined in this way in an inertial coordinate system is invariant under the Lorentz transformations. So, equation 1.1 is invariant under, this equation is invariant under Lorentz transformations. Or we can define Lorentz transformation to be the ones that leave this interval ds square is equal to c square dt square minus dx square minus dy square minus dz square invariant. So, in special theory of relativity, we have a space-time with an invariant interval given by this form: ds square equal to c square dt square minus dx square minus dy square minus dz square, or equivalently ds square is equal to dx4 the whole square minus dx1 square minus dx2 square minus dx3 square. Now we look at the kind of coordinate transformations that leave this interval invariant. First of all, we could see that this is equal to c square dt square minus of dx square plus dy square plus dz square. So any coordinate transformation that leaves dx square plus dy square plus dz square invariant also leaves the interval invariant. Obviously, rotations in space, the spatial rotations leave this quantity invariant. So are reflections about, say, x plane, xy plane, yz plane, and xz plane, or inversion of the coordinates. So in general, rotations, spatial rotations leave this interval invariant because spatial rotations leave dx square plus dy square plus dz square invariant. So rotations in space, they include both proper and improper rotations. And the second set of transformations that leaves ds square invariant are the ones that leave dt invariant, dx invariant, dy invariant, and dz invariant separately. And they correspond to translations in space-time. So the origin of the space-time coordinate system is shifted by an amount given by, say, dx mu going to, say, dx mu plus the constant factors a mu. Sorry, x mu going to x mu plus a mu, which implies dx mu going to dx mu plus d of a mu, but a mu are constants and therefore the dA mu are 0, and under these transformations dx mu goes to dx mu, and that leaves ds square invariant. So space-time translations is also an example of transformations that leaves ds square invariant. Now there is a third kind of transformation that leaves ds square invariant, and they are given by boosts. Boosts are transformations between frames of references that leave with travel with uniform or constant relative velocity. So three kinds of transformations leave ds square invariant. In special relativity, the first are space-time translations, and second, rotations in space, both proper and improper, and the third one corresponds to boosts, which corresponds to transformation between inertial frames traveling with non-zero uniform relative velocity. Now, to fix the notations, we explicitly write the form of the boost transformation between two frames of reference that have a constant relative velocity along the x-axis. So assume that the frame s dash, which have coordinates given by the prime coordinates, say x dash, y dash, z dash, and t dash, is moving with a velocity along the x-axis with magnitude v with respect to the first frame s, in which the coordinates are given by x, y, and z. Then the coordinate transformation between them is given by x dash equal to gamma times x minus beta c t, where beta is the ratio of v to c. V from here is the speed of the frame s dash with respect to the frame s. Now gamma is defined as 1 by square root of 1 minus beta square, or 1 by square root of 1 minus v square by c square. So x dash is related to x and t in the following way: x dash equal to gamma x minus beta ct, and y dash equal to y, z dash is equal to z, and ct dash equal to gamma times ct minus beta x. Or in terms of the notations that we used earlier, where we called x as x1, y as x2, z as x3, and ct as x4, we may write these transformations as x1 dash equals gamma times x1 minus beta x4, then x2 dash is equal to x2, x3 dash equal to x3, x4 dash is equal to gamma times x4 minus beta x1. Now x2 dash and x3 dash does not have any change in the values of the coordinates. So only x1 dash and x4 dash are different from x1 and x4. And the transformation can now be written in terms of a 2 by 2 matrix connecting these coordinates. And I write it as x1 dash x4 dash, the column vector, is equal to the matrix gamma minus gamma beta minus gamma beta gamma x1 x4. So the space-time coordinates are given by x mu, with mu running from say 1 to 4, and then ds square is now written as minus dx1 square minus dx2 square minus dx3 square plus dx4 square. Which can be written in the following way: g mu nu dx mu dx nu, where g mu nu in the matrix form can be written as minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 1. It's a diagonal matrix with diagonal entries. The first three diagonal entries given by minus 1 and the fourth one by 1. So it could also be equivalently represented using the following notation. Since it's a diagonal matrix, we will write it diag. Then we simply write the diagonal entries. They are minus 1, minus 1, minus 1 and 1. So this is also equivalent to this matrix. Now, space-time is a four-dimensional space, and x mu are the coordinates, and from our discussion on tensors, we know that the coordinate differentials are contravariant vectors, and therefore dx mu and dx nu are contravariant vectors, and the components of the contravariant vectors, ds square is a scalar, it's an invariant quantity, and the inner product of dx mu with g mu nu and dx nu with dx mu with g mu nu is a scalar quantity, which then imply that g mu nu is a tensor of type 0, 2. In fact, since dx mu is a symmetric tensor, we see that g mu nu can always be taken to be a symmetric tensor of type 0, 2. So it has a contravariant rank 2 and it is symmetric. And this tensor is called the metric tensor of the space. So g mu nu given by this expression in inertial coordinates is the metric tensor of the four-dimensional space-time in special relativity. And a four-dimensional space with a canonical form of the metric tensor given by this equation is called a Minkowski space. So the space-time in special relativity is a Minkowski space, and its metric tensor in the inertial coordinate system is given by this. So to distinguish it from the metric tensor of general spaces, in future classes we call it as eta mu nu. So this corresponds to this particular form. This corresponds to eta mu nu correspond to the metric tensor of the Minkowski space. Now for light which travels with the speed of light, with speed of light given by c, obviously ds square is given, can be found in the following way. So taking dt square outside, dt square c square minus of dx square dx by dt square plus dy by dt square dz by dt square. But this is the mod square or the norm square of the velocity of a moving particle. Now here light is the one that is moving, and it is moving with a speed equal to c, and therefore this quantity is equal to c square, and therefore ds square is equal to dt square minus c square minus e square, which is 0. So for light along its trajectory between any 2 points, we have ds square is equal to 0. So starting from a given event in the space-time, we can think of the set of all events for which ds square is equal to 0. And a world line along this subset of the space-time correspond to the world line of light, a possible world line of light, and for all of which ds square is equal to 0. And such a subset is called the light zone, light cone. Now, if we think of space as a one-dimensional space and time also as one-dimensional, the space-time can be thought of as two-dimensional. One dimension corresponding to space and the other corresponding to time. And in this two-dimensional space, the interval become ds square is equal to c square dt square minus say dx square. And for light, ds square is equal to 0, or in other words, dx is equal to plus or minus c dt. So, the light cone which is given by this correspond to two lines here. One corresponding to dx is equal to c dt and the other one corresponding to dx is equal to minus c dt. And starting from the given point, these can be represented by two lines. This line corresponding to x is equal to ct and the other one corresponding to x is equal to minus ct. So that dx equal to minus c dt for this line and dx is equal to c dt for this line. So these two lines represents the light cone in this two-dimensional space-time. Now if we assume that the space is two-dimensional, the figure gets changed to this one, where instead of these two lines, we now have a cone, and all points on this cone will have ds square is equal to 0. Now we can extend our imagination and think of a similar situation in the four-dimensional space-time, where the space is three-dimensional and time is one-dimensional. And the set of all points, the set of all events in the space-time for which ds square is equal to 0 form the light cone. Now obviously, the points interior to the light cone is these points. For them, the speed will be less than the speed of light, and therefore ds square will be positive. And they will be called time-like region. And for points like this that are exterior to the light cone will have the speed of particles greater than the speed of light, and for those regions ds square will be less than 0 and they will be called that will be called the space-like region of the space-time. The world line of a particle always lies within the time-like region of the space-time. So this way of classification of regions of space-time is very different from the classification where we can slice up the four-dimensional space-time into regions of three dimensions, three-dimensional events corresponding to the same value of the time coordinate. Now we come back to the geometry of the Minkowski space-time. We have already seen that the space-time interval is given by ds square is equal to eta mu nu dx nu, where eta is the metric tensor, and it is given by the diagonal matrix with the first three diagonal elements equal to -1 and the fourth one equal to 1. Obviously, the determinant of this metric is -1. Now, eta is a symmetric covariant metric tensor, and we can find its conjugate metric tensor the following way. Eta mu nu, the mu nuth element of the conjugate symmetric metric tensor, is equal to the cofactor of this metric tensor corresponding to the row mu and column nu divided by the determinant of this metric. So if we compute the corresponding cofactor, we will see that that is equal to minus eta mu nu, and this divided by -1, because the determinant of this is -1, and therefore we can see that the conjugate symmetric metric tensor or the contravariant metric tensor has elements, the mu nuth element of which is exactly the same as the mu nuth element of the covariant metric tensor. So the relationship between the covariant and contravariant metric tensor is the following. So eta mu nu and eta nu rho should be equal to delta mu rho. Now, writing the contravariant metric tensor as this, we see that the two matrices are the same, and multiplying these two matrices, we see that the result is simply the identity matrix, and which is given by this equation. Now, we can raise or lower the indices of any tensor defined at any point on the Minkowski space using the covariant and contravariant metric tensors. We can lower the index by using or forming inner product with the covariant metric tensor, and we can raise the index by forming inner product with the contravariant metric tensor. That is, given the coordinate differentials dx nu, which are components of a contravariant vector, we can find a corresponding covariant vector by forming the following inner product. We take the covariant metric tensor eta mu nu and form inner product with the contravariant coordinate differential dx. So eta mu nu dx nu, and the free index is mu, which is a covariant index. So we get dx mu. So that is the definition of dx mu. Now, similarly, given the covariant coordinate differential, we can obtain the coordinate differential with the contravariant index the following way. We form an inner product with the contravariant metric tensor. So eta mu nu dx nu, forming inner product, and the free index is mu, which is a contravariant index. Therefore, we will have dx mu. Now, the space-time interval can be rewritten in the following way. ds square was defined to be eta mu nu dx nu dx nu. But now the inner product of eta mu nu with dx mu is the same as eta nu mu dx mu, and this is because eta mu nu is equal to eta nu mu, eta being a symmetric tensor. But this is exactly same as the covariant coordinate differential dx nu, because it's an inner product and the free index is nu, we have dx nu. So we have this interval written as dx nu dx nu. Or equivalently, we can also do the following. We can take the inner product of eta mu nu with dx nu, but that is equal to dx mu, the covariant coordinate differential, and that's what I have written here. And this dx mu remains. So this will be equal to dx mu inner product with dx mu with a covariant index. We now discuss what is called proper time. Let ds square be the space-time interval between two events on a time-like world line. And since it is a time-like world line, the interval ds square will be greater than 0. And then the proper time interval d tau between the events is defined to be ds square equal to c square d tau square, where d tau is the proper time interval. ds square is positive, c square is positive, and therefore d tau square will be positive. And we can take d tau to be square root of that positive quantity, which will still be a real number. Now ds square in an arbitrary inertial frame of reference is given by c square dt square minus dx square plus dy square plus dz square. So the proper time interval d tau is defined by this equation: c square d tau square equal to c square dt square minus dx square plus dy square plus dz square. Now consider an inertial frame of reference in which dx equal to 0 equal to dy equal to dz. So in that frame of reference, the spatial difference between the two events is nil. That means in that frame of reference, the two events correspond to events corresponding to the same spatial points. They are separated only in time coordinates. So in that frame of reference, from this definition, c square d tau square is equal to c square dt square, because dx, dy and dz are 0, which means d tau square equal to dt square. To see where this situation arises, consider the world line of a particle which is moving with a constant uniform velocity, with respect to the chosen frame of reference, chosen inertial frame of reference. So we have an initial frame of reference in which we have the coordinates t, x, y, and z. The time interval is measured as dt, spatial intervals as dx, dy, and dz. In this frame, the particle is moving with a constant velocity. Let us call it v. Now consider an inertial frame attached to this moving particle. It is inertial because the particle is moving with a uniform velocity with respect to an inertial frame of reference, and therefore the frame of reference attached to this particle is also an inertial frame. But in this frame of reference, the particle is at rest, and therefore dx equal to 0, dy equal to 0, and dz equal to 0. So, in that case, c square d tau square will be equal to c square dt square, as we have seen over here. Or in other words, d tau square is equal to dt square, where dt now is the time measured by a clock attached to the second frame of reference. That is a frame of reference attached to the particle moving with that particular velocity at exactly the same spatial position as the event. Therefore, we may consider the proper time interval between two events as the time interval measured by a clock that is moving with uniform speed between these two events. In other words, it is the time interval as measured by a clock which is at rest with the moving particle, the particle being in motion with a constant or uniform velocity. We now consider the relation between the time interval in a frame and the proper time interval. Consider two events separated by coordinate differences dx, dy, dz and dt in a frame S on the world line of a particle which is moving with a velocity v. So the instantaneous velocity is given by dx by dt, dy by dt and dz by dt, the three spatial components of the velocity. And this is the velocity in the frame S. The proper time interval between these events is defined as c square d tau square equal to c square dt square minus dx square minus dy square minus dz square. Now taking c square dt square outside, we have c square dt square. Then from the first term, we have 1 minus 1 by c square times dx by dt square, dy by dt square plus dz by dt the whole square. But now this is equal to the x component of the velocity, this is the y component of the velocity, and this is the z component of the velocity of the particle, or the frame of reference attached to that particle. So this is equal to c square dt square minus times 1 minus v square by c square. Now defining beta as v by c and gamma as 1 by square root of 1 minus beta square, we have from here c square d tau square equal to c square dt square by gamma. So cancelling c, we have d tau equal to dt by gamma. So this is the relationship between the proper time interval and the time interval measured in an inertial frame that is moving with a velocity v . So if the time interval measured in a given frame of reference, inertial frame of reference is dt, between two events on the world line of a particle moving with a velocity v, then the proper time interval is given by dt by gamma, where gamma is given by this expression. We now discuss four vectors. The space-time in special relativity is a four-dimensional space, the Minkowski space. It's characterized by a metric eta, which in the inertial coordinates is given by a diagonal matrix with the first three diagonal entries equal to -1 and the fourth one equal to +1. So it is independent of the spatial points, and we immediately see that the curvature tensor is 0 for this metric. And therefore, Minkowski spacetime is a flat space. Now, at every point on the space, we have a tangent space, which correspond to the set of all possible vectors that can be defined at that point. And these tangent vectors on the four-dimensional Minkowski spacetime are called four-vectors. That is, four vectors are tensors of rank 1. We now consider some of the examples of four vectors. The first one we consider is the four velocity. Now consider the world line of a particle, and the coordinates of the particle are given by x mu, x1, x2, x3 and x4 in an inertial frame. The world line of the particle can now be parameterized by the interval s, because s is an invariant quantity, a scalar quantity. And equivalently, since s is related to tau, as ds equal to c d tau, or ds square is equal to c square d tau square, we can also parameterize the world line by the proper time tau. So we may write along the world line the coordinate of the particle as x mu equal to x mu of tau. Now the coordinate differentials dx mu are the components of a contravariant vector, and since tau is an invariant quantity, dx mu by d tau is also a component of a contravariant vector. So we may define a new vector, contravariant vector, with components u mu equal to dx mu by d tau. So these are the vectors tangent to the world line of a particle that is parameterized by the proper time and are called the four velocity, the components of the four velocity. Now to find how the four velocity is related to the velocity measured in a particular inertial frame, we consider its definition dx mu by d tau. Now d tau is related to the time interval measured in that particular frame as d tau is equal to dt by gamma, where gamma is equal to 1 by square root of 1 minus v square by c square, where v is the velocity of the particle. So tau can be written as a function of time in that particular frame of reference, and therefore we may write d by d tau is equal to dt by d tau times d by dt. So we have dx mu by d tau equal to dt by d tau times dx mu by d tau. Now as we have already seen, d tau is equal to dt by gamma, or dt by d tau is gamma. So this factor is gamma. And dx mu by dt is actually the velocity component measured in that particular frame of reference, and we call it as v mu. So we have the following identity: u mu equal to gamma times v mu, where v mu are the components of velocity measured in a particular frame of reference in which the particle is moving with a velocity v, and in terms of v we have defined gamma to be equal to 1 by square root of 1 minus v square by c square. Now the components of the force velocity u mu are given by u mu equal to gamma times v mu. Explicitly, u, which is a 4-component contravariant vector, u1, u2, u3, u4 are given by gamma times dx1 by dt, dx2 by dt, dx3 by dt, and d by dt of ct. Now c is a constant, and therefore d by dt of ct is simply c. So the force velocity is simply gamma times v1, v2, v3 and c. And since we know the structure and the metric tensor of the Minkowski spacetime, we can consider two force vectors a mu and b mu, and their inner product can be defined as a dot b is equal to a mu b mu, which can also be written as a mu eta mu mu a nu eta nu mu times b mu, and that is because this is equal to a mu. Once we define the inner product of two vectors, we can define the norm of the vector using that inner product. Now, the norm square of a vector A is defined as the inner product of the vector with itself. So, norm square of A is equal to a mu a mu. Now, we can compute the norm of the force velocity. So, this will be norm of the force velocity u mod square will be equal to u mu. We already know what the contravariant force vector u mu is. Now to find the corresponding covariant counterpart, we have to write u mu as eta mu nu u nu. So this should be nu. So that means eta mu nu is a diagonal matrix. So only when mu is equal to nu is this non-zero, and therefore we get this as u mu as this is equal to, for the first three, that is for mu equal to 1, 2 and 3, this is non-zero only when nu is equal to 1, 2 or 3. So u1 is equal to eta 1 nu u nu, but this is equal to eta 1 1 u1 plus eta 1 2 u2 and so on, but eta 1 2, eta 1 3, eta 1 4 etc. are 0. Now eta 1 1 is minus 1, and therefore this is equal to minus 1 times u1. But minus 1 times u1 is simply minus gamma times v1. And that's what we have written here. Similarly, u2 is equal to eta 2 nu u nu, but then only eta 2 2 is non-zero, and that is equal to minus 1. So we will get minus u2, which is minus gamma v2, and that's this. And similarly we get minus gamma v3 for u3, and for u4 we have eta 4 u4, but this is equal to eta 4 is 1. So 1 times u4, but u4 is equal to gamma times c. So that's what we have got here. Now that we found the covariant counterpart u mu of the 4 velocity, we can find the norm of the 4 velocity u. So this is equal to u mu. So that's equal to u1 plus u2 plus u3 plus u4. Now this is equal to minus gamma v1 and this is equal to gamma v1. So the first term will give me minus gamma v1 square and the second term will give me minus gamma square v1 square and the second term will give me minus gamma square v2 square. Third one minus gamma square v3 square. So these first three terms will give me minus gamma square times v1 square plus v2 square plus v3 square. And the fourth term, and this is gamma c and the other one is also gamma c, we will get gamma square c square. And that's exactly what we have got here. Gamma square c square minus this gamma goes inside gamma square times v1 square plus v2 square plus v3 square. But this is nothing but the magnitude square of the velocity and which we denote by v square. So we have u norm square is equal to gamma square times c square minus v square. Now taking c outside, we have gamma square c square times 1 minus v square by c square. But 1 minus v square by c square is 1 by gamma square. So cancelling with this gamma square, we get the result as c square. So we immediately see that the magnitude of or the norm of the 4 velocity is equal to c, or the norm square of the 4 velocity is c square. Now, along the world line, the 4 velocity can change. So consider the world line of a particle, and since the world line is parameterized by the proper time tau, the 4 velocity along the world line will also be parameterized by the proper time tau. So we may write u mu as u mu of tau. So for every value of tau, there will be a point on the world line of the particle, and u mu of tau is the 4 velocity of the particle at that particular event. Now we also know that the norm square of u, which is given as u mu equal to c square. Now taking the derivative with respect to tau, we have d u mu by d tau times u mu plus u mu times du mu by d tau, which is equal to d by d tau of c square. Now c square is a constant and its derivative with respect to tau is 0. Now we consider this second term u mu du mu by d tau. But then this u mu can be written as the inner product of eta mu nu, the contravariant metric tensor, with u nu times this. Now eta mu nu in inertial coordinates is given by a constant metric, and its derivative with respect to tau is 0, and therefore it can be taken inside the derivative, and we get this to be equal to u nu d by d tau of eta mu nu u mu. But this is nothing but u nu, the contravariant for velocity component. So we see that this quantity is nothing but this quantity, but now calling nu as mu, we get that to be exactly equal to u mu du mu by d tau. So that means this second term over here is exactly same as the first term. And then this equation becomes 2 times du mu by d tau times u mu is equal to 0, which implies that u mu du mu by d tau is equal to 0. But this look like the inner product of two tensors, provided this is also a tensor. In general spaces, this derivative may not be a tensor, but Minkowski spacetime is flat, and therefore the intrinsic derivative of a contravariant vector with respect to a parameter tau is the same as the ordinary derivative, and therefore this is the inner product of u mu with a tensor given by du mu by d tau, and therefore this is sort of the inner product of these two tensors. And we may say that the inner product of u with the derivative of u with tau 0, or in other words, u and du by d tau are orthogonal to each other. And a second example of the four vectors is the four momentum, which is defined to be p mu equal to m0 times u mu, where u mu are the components of the four velocity, and this quantity m0 is the mass of the particle in a frame in which it is at rest. So it is an invariant quantity. So p mu can be written as the four components written as m0 u1, m0 u2, m0 u3, m0 u4. Now u1 is gamma v1, u2 is gamma v2, and so on, and therefore p mu can be written as m0 times gamma with components v1, v2, v3, and c. Now the corresponding covariant vector p can be found using this formula, and we get it to be equal to m0 gamma times minus v1 minus v2 minus v3 times and c. And its norm can be computed as norm square of p is p mu, which is equal to m0 u mu, m0 u mu. M0 is an invariant quantity, so m0 and m0 is m0 square, then u mu. So this is nothing but the norm square of the four velocity, which we knew, which we found to be equal to c square, and therefore the norm square of the four momentum is equal to m0 square c square.